don't forget. Okay, so today we're going to review chapter 3. So your guys' exam is tomorrow, if I'm not mistaken, and all your quizzes and everything. So today's worksheet I had wanted to cover, but what we've been doing for the past 2 weeks. So I have some questions on molar mass, percent composition, balancing equations, and then doing stoichiometry with some different equations. Now, I wanted to remind everyone that you may be just following the SI worksheets here on my screen, but I do post them online. So if you want to follow the worksheets on your own, or if you want to use the worksheets as practice problems to go back and study, I'm going to put the link to the SI website in the chat. So you can go to that website and follow, just scroll down to the bottom of the page, and all of the worksheets that I show you guys are on there. So you can go back and redo them if you want. Let's see. I think that's all for a little housekeeping stuff. What questions do you guys have before we start today? Okay, so as always, if you could just go in the chat and drop down. Oh, sorry, we got a question. Are the answers anywhere so we can check our work? Yes, so what I can probably do is go through all of these worksheets I have here and make PDFs of all of these, and then post the answers on the SI website. So the link that I put in the chat, after this, I will take all of the worksheets for chapter 3, make PDFs of them, so you'll have the answers, and then I'll post them on that website. Does that sound okay? All right. So yeah, if you could just drop your Iowa State net ID in the chat, that would be great. So let's go ahead and begin today. So the first 3 problems, checked off attendance, I can erase that. Last thing I want to remind everyone is this relationship. Now, you've seen this a few times now. And just to refresh your memory, so there's 3 states we can have. We can have grams, we can have moles, and we can have atoms and molecules. Now, you can go between these on the line using, from moles to grams, you use the molar mass, which is measured in grams per mole. And this comes from the periodic table. And if we want to go from moles to atoms or molecules, we have to use Avogadro's number, which is always the same number, and that is 6.02 times 10 to the 23rd. So I'm sure you have this written down somewhere, but if you don't, take a picture of this, and we're going to be using that today and on your quiz and exam. So in that case, go ahead and start on questions 1 through 3. Let me know what questions you have as you're working, and then we'll come back together in a few minutes. So as you continue working, I just want to make sure everyone's getting the same chemical formula for number 1 and 2 before you start looking for the molar mass. So sodium carbonate, let's review how you get sodium carbonate, the chemical formula. So we have sodium, which is Na, and we have carbonate. Now carbonate is not an element, that is a polyatomic ion. So let's cruise over to the polyatomic ions chart. Now, if you don't have the polyatomic ions chart, I recommend you take a photo of this. Now, these are, to review polyatomic ions, they are common covalent molecules that are so common that they just get their own name. So I put X's next to the common ones here. Something like NO3 minus is so common that we just call it nitrate. SO4 2 minus is so common, we just name it sulfate. So what you do is you come to this list and say, well, where's carbonate? Okay, here's carbonate. And the chemical formula is CO3 2 minus. So let's go back to our worksheet. So CO3 2 minus charge. So now the question is, if we're going to build some sort of ionic compound out of this, what is the charge on the sodium? Does anyone remember how you get the charge on the sodium ion?
It depends on like the group that they're in, right?
Yeah, so where would you find that, Kristen?
I just remember there was a slide in the lecture where it had like the charges of some elements, so I just look at that.
Okay, right, so it depends on the group. In other words, it depends where it is in the periodic table. So to review, every column has a charge. So a +1, +2, +3, and then this column is sort of like in between, plus or minus 4. And then we start going down -3, -2, -1, and then the last column is 0. So all of the elements in this column, let's take the first one, for example, because our sodium is right here. All of the elements in this column will all have a +1 charge. And that applies for every column you go across on the periodic table, except these ones here in the middle. We say these ones have a variable charge. And these are the transition metals. So you can't tell from the periodic table. But for our case, sodium is right over here. It is in the first column, therefore it has a +1 charge. So we are going to write down +1 here for sodium. Now we have to build our chemical formula. And to do this, we need to swap our charges and build our ionic compound. So the number here is going to become the subscript down here, and the number on the CO3 is going to become the subscript here. What does this look like? Well, this would be, let's do it in red. So Na, and we have CO3. So we take this 2 here from the CO3 as a charge of 2 minus. This goes down here, Na2. And the sodium has a charge of 1, so the CO3 gets a charge of 1, or a quantity of 1. So we're taking the 2, put it down here, and the 1, we put it over here, just swapping the numbers. Now, of course, we don't ever write 1, we just kind of leave that off. So Na2CO3. Now let's get the name for number 2, and then I'll give you a couple more minutes to try to find the molar mass and the percent composition. So we have iron 3 chloride. Okay, so what are the 2 elements? We have iron, which is Fe, and chloride, which is chlorine, which is Cl. Now, how do we find these charges? Well, again, let's look at the periodic table. Where is chlorine? Chlorine is box number 17 right over here. And this is in the -1 column. It's in this column right here. Therefore, chlorine has a -1 charge. -1. What is the charge for iron? Well, let's look on the periodic table again. Iron is right here in the middle. Now, iron is in this, excuse me, in the transition metals, which has variable charges. So we can't read this off the periodic table. So who remembers how we find the charge of iron in this case?
It's the Roman numerals following the name iron.
Okay, so it looks like Isabel said is the Roman numerals here. So that's exactly right. These numerals here is the charge on the iron. So that's a +3. The transition metals, you always have to put a Roman numerals with the numerals representing the charge on the cation, because you can't get it from the periodic table. So let's take the 3 here, and we're going to put that on the chlorine, and the 1 here and put that on the iron. And our formula should be Fe1Cl3. Now, once again, we never write the 1 here, so it's just FeCl3. Okay, and then why don't I give you about 1 more minute or so and see if you can grab the molar mass and the percent composition now that you know the formula, and then we'll do it together in just a minute. Okay, we will continue doing this together. If you didn't get it completely finished, that's totally fine. So we have sodium carbonate, and we're trying to find the molar mass. Now, what you got to do is find each of the individual masses from the periodic table. Now, we have 3 elements, sodium, carbon, and oxygen, so I wrote those here. And then we are going to get their masses from the periodic table. So sodium has a mass of, it's right here on the left, it has a mass of 22.99. So we're going to write that right here, 22.99. And I'm literally getting the number straight from the periodic table. Carbon is 12.01 and oxygen is 16.0. So I'm going to put those here, 12.01 and 16.0. Now I'm going to times these by the number there are in our compound. So we have 2 sodiums in our compound, so times by 2. We have 1 carbon, so I'm going to times this by 1. And we have 3 oxygens, so I'm going to times oxygen by 3. And this will give us 45.8, 24.02, and this one is 48.0. So once we have those, we want to add them up, and this will give us a total molar mass of 105. It's So 105.81. And the units for molar mass is grams per mole. And that will be the total molar mass for sodium carbonate. Okay, moving on to FeCl3. So we're going to do the same thing. So we have Fe and Cl. And we're going to grab the numbers from the periodic table. So iron has a molar mass for itself of 55.85. And chlorine has a mass of 35.45. And we're going to times these by the number we have in our compound. So that's 1 iron and 3 chlorines. Now this is going to give us 55.85 for iron. And for chlorine, it's 106.35. Now when you total these, you will get a total molar mass of 162.20 grams per mole. Now number 2 was not asking what is the molar mass. It was asking, move these down a little bit, it was asking what is the percent composition of each element by mass. So I'm going to draw a little line here to separate. So to get the percent composition of each element, so we're going to do iron first. This is going to be the amount of iron that we have divided by the total molar mass. So the amount of iron we have is 55.85. And the total mass we found was 162. So 55 for the iron right here, and the total is 162. And then since we're doing a percent, we have to times by 100 to go to percent. And this will tell us we have a mass, a percent composition by mass of iron as 34.4%. Now, to find the percent composition of the other one, which was chlorine, you could just do 100% minus 35, but I'll do the calculation just so you know, just so you get to see how to do it again. So we take the mass of chlorine in this compound, 106, and divide by the total, 162.20, and then times by 100 to go to percent, and that will come out to 65.6%. And would you look at that? They add up to 100. So a good way to check is if they don't add up to 100%, you know you have to do something, have to have done something wrong. What questions do you have on numbers 1 and 2?
If they don't give a correct number of sig figs, what do you think we should do? Should we do like to 2 decimal points, or what do you think we should do for that?
Yeah, that's a good question. So in this problem, it didn't specify sig figs, so it's a little ambiguous. That would be well, you're not going to be taking the test in person. There's going to be 2 things. A, it is either going to specify use 4 sig figs or use 3. If not, then I would go based on the number of significant figures on the periodic table. So if the periodic table had 4 sig figs, then I would put 4 in my answer. And at least that way, you would be able to argue to your professor, look, I was just using the number of sig figs on the periodic table that you provided for the exam. But I'm hoping that they're going to be a little more explicit with the number of sig figs. Did that help a little bit?
Yeah, thank you.
Okay. All right, and let's do number 3, since that was one of the other questions up there. So what is the balanced chemical formula for the complete combustion of propane, C3H8? Okay, so let's write down C3H8 plus, well, what else goes here? So this, you have to remember, what is the formula the general formula for a complete combustion, that would be you're adding O2 and you're going to CO2 and H2O. This is always the form for complete combustion reactions. It's always going to be some sort of fuel plus O2 goes to CO2 and water. Now, what I like to do to balance equations is under the arrow, I like to draw a line or a little chart like this and count the number of atoms on both sides. So on the left side, we have 3 carbons, and write that here. We have 8 hydrogens, and we have 2 oxygens, so 2 there. On the right side, we have 1 carbon. We have 2 hydrogens here. And the oxygens, we have 2 plus 1, so that's 3. Now, just by looking at this chart, we know we need more carbons on the right. So we need 3 carbons on the right. So we have to put a 3 in front of this. The only way you adjust these formulas are by putting coefficients in front of the chemicals. So this would mean we now have 3 carbons on the right, so 3 here, but we also upped the number of oxygen. So we have 3 times 2, this is 6 oxygen, plus another one, that's 7. So 7 oxygens. Okay, moving on. So our carbons are equal. Now we need hydrogens balanced. So we need more hydrogens on the right. We have 8 on the left. So I'm going to put a 4 here. And so that is going to mean that the hydrogens on the right is 4 times 2 is 8. 8 hydrogens. And now we also adjust the number of oxygens. So 4 oxygens here plus 6 oxygens here, that would be 10 oxygens. So now our oxygens are off balanced, so we need more oxygens on the left. So here we can put a 5 in front of the O2s, and this will make the 5 times 2 oxygens makes this side 10. So now our carbons are equal, hydrogens are equal, and oxygens are equal, and you have completed your balanced chemical equation. What questions do you have on number 3? Okay, so let's move on, and I accidentally covered up a few of these problems. So there we go. So go ahead and work on, I'll try to leave the work up for the last one. Go ahead and try to work on 4, 5, and 6, and we'll come back together in a few minutes.
I put a question in the chat.
Sorry, I didn't see that. I'll check that out. How did you know that was the full reaction of the previous question? So the way you know that your reaction is complete is that the number of atoms on the left side is the same as the number of atoms on the right side. So the way I keep track of that is by using a little chart like this, and I just count. When I think it's balanced, I just count and say, well, I have 3 carbons here. I should have 3 carbons on the right.
But like, how did you know to start with C3H8 plus O2.
Oh,
and then
okay.
O2,
Like where did the O2 and CO2 come from?
and the H2O. Yeah, like how did you know all that?
Okay, I'm going to I'm going to jump onto the yesterday's worksheet real quick, and if you want to look at this real quick. So these are the general forms for the equation. So if you want to take a picture of this.
Okay.
So a complete combustion is some sort of fuel plus O2 goes to CO2 and water.
Okay.
And so these are 6 common chemical reaction types that we deal with in this class. And so there's always just a general formula. In this case, we were told it was a complete combustion reaction. Therefore, it has to follow this formula here. Does that make sense?
Yes.
Okay, great. Okay, let's start going over 4, 5, and 6. So number 4 says, how many molecules are there in 10 grams of dinitrogen monoxide? So once again, I didn't give you the chemical formula. I expected you to get that from name, and that is free game on the exams as well. So this is a molecular compound, and we know that because it's 2 nonmetals. Nitrogen and oxygen are both nonmetals. In other words, they're all on this part of the periodic table. So the nonmetals are up in this corner. So nitrogen and oxygen are both up here. Therefore, we know this is a molecular compound, which means that the prefixes determine the number in the chemical formula. So dinitrogen, that means 2 nitrogens. Di means 2. And then monoxide, that means 1 oxygen. Mon is, think about like mono, right? 1. So we have N2O1, or we just write that as N2O. Okay, so now to figure out how many molecules there are in this. So we start with 10 grams of N2O, and we are going to convert this to moles. So I have grams on top. Let me zoom in a little bit here. I have grams on top, so I want to put grams on bottom so that it cancels. And we are going to go to moles on the top because we can't get to molecules but without first going to moles. So what numbers go here? Well, this is the molar mass. So we do just like we did in the first problems, but we do N2O molar mass, and that is 44.02. Is that correct? Or did I add that up wrong? Let's see. No, that's right. Okay, so, and then you know you're doing it right because the grams N2O cancels top and bottom. Now, what is the conversion between moles and molecules? Well, this is where we use Avogadro's number. So we put moles N2O on bottom so that it cancels. and we put Avogadro's number on top. 6.022 times 10 to the 23rd. And the unit for this is molecules of N2O. There are 6.02 times 10 to the 23rd molecules of N2O in each mole. So again, moles cancel, and you're left with just molecules. Now, multiply the numbers on the top and divide all the numbers on the bottom. And make sure you're able to do this with your own calculator. And I recommend you try it out on your own. And I got, this was 1.37 times 10 to the 23rd molecules. And the original problem had 3 sig figs here, 1, 0, and 0. That's 3 sig figs. Therefore, the final answer should have 3 sig figs as well. So 137 is 3 sig figs. Okay, on to number 5. So how many hydrogen atoms are there in 2.75 moles of water? So again, here we need to know what the chemical formula for water is. This one should be pretty obvious, H2O. So how many hydrogen atoms are there? So start with 2.75 moles of H2O. And we want to go to, I want to use Avogadro's number to get to molecules. So we put moles on bottom so that it cancels on top. And we're going to go to 6.02 times 10 to the 23rd. And the unit here is molecules of water, or molecules of H2O. Now, why is it molecules of water, not atoms of hydrogen here? That's because, maybe I'll write H2O here. H2O, molecules of H2O. It's because the unit here is H2O. Therefore, the unit on top is still going to be H2O. We have to do another step still to get to atoms of hydrogen. So let's continue our bar and write molecules of H2O on bottom so that it cancels on top. And this is where we do our conversion to atoms of hydrogen. So how many atoms of hydrogen are there in water? Well, it's just 2. That's what the 2 in H2O means. It means there's 2 hydrogen atoms in each molecule. So once again, H2O means that there's 2 hydrogens in each molecule of water. So our units again are canceling top and bottom, molecules H2O. And again, just multiply the numbers on top and divide the numbers on bottom. And I got 3.31 times 10 to the 24 hydrogen atoms. And that would be the final answer. And just to review sig figs again, the original problem has 3 sig figs. Therefore, our answer has to have 3 sig figs. So 3, 3, and 1 are the digits. Remember that the times 10 to the part, this does not matter with sig figs. The only thing that matters is the part right before it, 3.31. What questions do you have on number 4 and number 5? Okay, so let's work on number 6. I'll move this down again. There we go. So number 6 says a chemist synthesizes phosphorus trichloride in a combination reaction by mixing 15 grams of white phosphorus, P4. So let's write down what we're starting with. We're starting with P4. And we're mixing that with chlorine gas. So Cl something. and this is a combination reaction. So the phosphorus and the chlorine are combining into one to make phosphorus trichloride. That would be PCl3. Now, I'm missing something. Something is incorrect in this. Well, it's not balanced for one, but there's something else here. Does anyone know what it is?
There needs to be 2 chlorine molecules.
So Emma, why does there need to be 2 chlorine molecules?
Because as a gas, chlorine has 2 molecules.
Okay, great. So yes, that is the key point to realize here. Is that here? I'll write down what they are. There are 7 atoms that in their natural state always come in pairs. And let's see, Cl2. To look at the periodic table. N2O2, F2, Cl2, Bri. Okay. F2, Br2, and iodine 2. So whenever these substances are on their own, they always come in, there we go. They always come in pairs, and we call these the diatomic, naturally diatomic molecules, or something like that. All you have to know is that chlorine is always 2 in pairs like that. Okay, now, once we have our reaction, we need to balance it. So what I got for the balanced reaction is, well, we need 4 phosphoruses on the right because we have 4 over here. So we had a 4, and then this would make us have 12 chlorines on the right. Therefore, we need to put a 6 here. So the balanced equation is P4, 6Cl2 goes to 4 PCl3. Ryan, I think what you did on yours is you may have balanced it correctly, but on the right side of your equation should be PCl3, not PCl2. Okay, so part A, this is part A here. Now, part B is how many grams of phosphorus trichloride is produced? Now, we were given 23 grams of chlorine gas and 15 grams of white phosphorus. What type of problem is this?
Is this a limiting reagent problem?
Yes, it is. And did I lag out? Oh, there we go. It is a limiting reagent problem. And how did you know that, Isabel?
To figure out how much of a product is produced, you have to figure out which reactant would determine how much product is formed.
Okay.
If that made sense, I don't know if it
Yes. Yep. That's exactly how you do it. So the way you know that this is limiting reactant problem is because it gives you 2 amounts of substances to start with. You're given 23 grams of chlorine, and you're also given 15 grams of the white phosphorus. So this is 15 grams here, and then this is 23 grams. Anytime you are given 2 amounts of reactants, you know it's a limiting reactant problem, and they will not tell you on your exam. Now, to do this, again, there's different methods to go about these. The way I do it is I do 2 separate calculations, but if you have a method that you prefer, feel free to stick to that. Now, I should write more specific here. 15 grams of P4, and then the second one is 23 grams of Cl2. And we are going to go to, let's see, what are we doing? Phosphorus trichloride. So let's do 2 calculations. And if you want to do your own method, you're going to get the same answer, assuming you're doing it correctly. So let's put grams of P4 on the bottom, so that cancels the grams on top. And then we'll put moles of P4 on top. So what is the grams of P4? Well, this is the molar mass from the periodic table. So this is 123.88 grams. So now we're at moles of P4. So this one's on top. I'm going to put that on bottom down here, moles P4. And I'm going to put moles of what we are trying to go to on top. So we're trying to go to phosphorus trichloride. I'm going to put that on top. So what is the conversion between P4 and PCl3? This is why we needed to balance the equation. So it is the numbers in front of each of these that determines the mole to mole ratio. In our case, the ratio of P4 to PCl3 is 1:4. I'm just reading a 1 here and a 4 here. Okay, and lastly, so we have mole PCl3 on bottom so that it cancels on top. And we put grams PCl3 on the top. And here, once again, we use molar mass, and you are able to get that from the periodic table. It's 137.32 grams. And if you multiply the numbers on top, divide the numbers on bottom, I get with 3 sig figs 66.5 grams of PCl3. Okay, and for B, well, we're still part B, but the chlorine, same thing. We're going to put grams of Cl on bottom, moles of Cl on top. And the conversion here is the Cl2, is the molar mass. Now, don't forget, it's Cl2, so you have to double the number on the periodic table. So this is 70.90. That's a 7 there. 70.90. Okay, so now we go mole to mole. So moles of Cl2 to moles of PCl3. So that would be 6:4. And then lastly, from moles to grams, so moles PCl3. And the same thing that we did up here, which is 137.32 grams PCl3. And this result comes out to be 29.7 grams of PCl3. So we have our two answers. Who remembers how we tell which of these is the correct answer?
Whichever one is smaller.
Okay, right. So Kristen said whichever one is smaller. So the smaller one needs between 66 and 29. 29 is smaller, therefore this is the answer to the problem. If you were asked what is the limiting reactant, that would be, the way you do that is you take the answer and then you trace back to the beginning what you started with. So come all the way back through here, and we started with Cl, therefore Cl2 is the limiting reactant. So just trace back to what you started with. And last thing I want to mention, I know it wasn't asked on here, but what would be the excess reactant? Well, it's always just opposites. So if Cl is the limiting, then phosphorus would be excess. Or the one that is left over at the end. What questions do you have on number 6?
Question about the excess reactant.
Yep.
Excess, would there be with
You're-
6.5 grams?
You're cutting out a little bit, Madison. I couldn't catch that. Do you want to maybe type it in the chat?
Would you mind going over how you get the excess amount for the phosphorus or not?
Yeah, yep. I can run through how you would do that. So I know the session technically ends at 5, but if you want to head out now, that's fine. Otherwise, I'll go over how to get the excess reactant. So let's add a part that says, I'm going to add a part that says, part C, how much excess reactant remains. So at the end of the reaction, how much excess is left over? In other words, how much P4 is remaining, because P4 is excess. So the way we do this is we take the we take the limiting reactant, the amount of limiting reactant, in this case 23 grams of Cl2. We know Cl2 is limiting, and we started with 23 grams. So I'll scoot down just a little bit here. And we are going to convert this to P4. So let's put grams of Cl2 down here and moles of Cl2 on top. So the conversion here is 1 mole is 70.90 grams of Cl2. Now we want to go to moles of P4. So moles of Cl2 to moles of P4. So we're going from the limiting to the excess. So what is the ratio here? Well, this is given in the original equation is 6-to-1 ratio. So that is 6 Cl2s to 1 P4. Now we go to grams. So moles of P4 to grams of P4. And the molar mass of P4 from earlier in our problem we know is 123.88. So I'll run this calculation. I didn't do this, but I'll do it real quick. And if someone else could do that and let me know if they get the same answer. So I got this to equal 6 point, well, we'll call it 6.70 grams. So 6.7 grams of P7 or P4. Who can tell me what this number means?
It's how many grams are left over of the white phosphorus in the reaction.
Very close. You're very close, Ryan.
Is it how much it was used? So then you need to subtract it from what was given.
Right. Yeah, there you go, Megan. So this amount is not the excess. This right, maybe a different color. This amount is the amount that is used. That's a terrible U. This is the amount that was used in the chemical reaction. But we were given 15 grams in the problem. The problem said we had 15 grams was given. Therefore, the amount that is left over, or the excess, is going to be the difference between these. So 15 minus 6.70. And that is going to be 6.3 grams. Is excess or leftover at the end. So question was, will the excess reactant stuff be on the test? I honestly, I can't, they won't tell me what's on the exam, but it is from previous semesters doing this, it has certainly been a topic that was fair game on the exam. So my recommendation would be study for it as if it was going to be on there. My experience is always, if I choose not to study for something, it just it never fails to show up on the test, and then I get screwed. So that's my 2 cents. Anyways, the session, I guess, is technically over. I hope you guys do well on your exam, and we'll see you guys on Monday. If you have any last lingering questions, feel free to stick around for a few minutes, and I can help you out. Oh, and one last thing. I will get these PDFs, the answer keys. I will post them on the SI website, and I'll try to get that done this evening, maybe around 6 or 7. All right, we'll see you guys later. You're welcome, Ryan. You're welcome, Isabel. Okay, Faith asked, why 6.3? So let's see here. So let's see, you can just type in the chat, Faith. Did you follow us to here? Were you following to here, or were you confused how we got to 6.7?
I was just wondering why like 6.3 and 6.7 don't add up to 15.
Oh, what the heck? Okay.
That's why I was confused.
Okay. Good point. Yep. So 15 minus 6.3, what is that? 8.7. No, wait, no, 15 minus
8.3.
7. 8.3, thank you. I must have done like 13 minus 6.7. Thank you for that.
Sorry.
Yeah.
Okay, I was just confused how you solve 7. Like I was just, or the second 6.
Oh yeah, yep.
Like how just to get started on it, because I was fine with the rest of the problems.
Okay, so this one we did, here we go. We did this one, let's see, last Thursday. So I'll post the answer key to this one, but let me walk you through how you would set this one up, Megan. So we are told that there's 82.6% of carbon by mass. Therefore, how would you find the mass of the hydrogen?
Would you just subtract it from 100?
Right, yep. So that would come out to be 17.37.
Okay.
Now, the chemical, this problem says it is only a combination of carbon and hydrogen. And these X's here, we're trying to find the number on what the number is for those X's. So for example, it could be C5H10 or something like that.
Okay.
So are you following so far?
Yeah.
Okay. So what the process you take is you take the percentage of each element, 86 or 82.6 and 17.37, and you divide each one by its own molar mass, the number from the periodic table. And that will give you an amount of moles, a hypothetical amount of moles in this compound. So this would give you 6.8 moles of carbon and 17 moles of hydrogen. Are you following still this far?
Yeah.
Okay.
Oh, and then you divide by like the least one to get.
Yes.
Okay.
Yes.
And then from there, okay. Okay. I did some of the homework problems. I think I was just confused with how to set it up. So.
Okay. Great. But does the rest of it make sense then for you?
Yeah, so the empirical one is it's like the simplified version of the molecular.
Yes, that's
right.
Yep.
So, but to go from empirical to molecular, I forget how you do it.
So there's got to be some sort of information given to you in the problem. In this case, just about beat this number to death, but 58.14, if you can still see this, it says it should have a molar mass of this.
Oh, okay.
But the question is, based on what we found for the empirical C2H5, what is its molar mass? Yeah, you can try to grab it from the periodic table if you want, but I wrote it right here.
Okay.
So
I'll
its
just
molar
look
mass
at it.
is 29. Now there's some relationship between what it is and what it should be. And to find the molecular, it's just finding what is the relationship between the molar masses.
So divide 58.14 divided by 29.7. So yes, 2.
Yeah, so what would you do with that 2?
You would take the C2H5 and just double the subscripts.
Yes, exactly.
Okay, that makes sense. Thank you so much.
Okay, you're welcome. Good luck tomorrow.
Yeah, thank you.